So to understand that, we'll start by discussing the variance of the coefficients themselves, their sampling variability. So the coefficients are random variables because the data are random. So you can imagine, before we started doing linear regression, we were just looking at stuff like this, where we have some data generating process where x is sampled according to some distribution, and then we have y given x is sampled according to some distribution, conditional distribution. Now you can imagine just adding to that data generating process this other random variable beta hat, which is not sampled from some distribution, but is some deterministic function of what x and y are. But because x and y are random, this thing is also random, right? So that's another way of looking at it. So let's just see that for ourselves. So here, pause the video, see if you can just do the simulation yourself. You should be able to at this point with the tools that we've kind of built up previously. So this is like what we were doing in lecture 7 or 6, where we're just building sampling distributions. So here, this is the data generating process. I'll do it in R, but you should give it a shot yourself. Okay, so now I can generate a data set like this. So we got a data set with 200 rows, x and y. So this is done. And now let's do linear regression. So this is just a review of what we talked about last time. So we can use the lm function in R. And these are the coefficients we get. Cool. So just to show you that these numbers are random, let's say we did not have this particular data set, but we got a different data set from the same population. We rerun that to simulate that process, and then we rerun this, and you see, hey, we get different values, right? So these estimates, like any other estimate, like a sample mean or a sample covariance or whatever. These are estimates. They're just a little more complicated in how they were constructed. It's not just take the average of some numbers. It's this more complicated process of taking the data, doing gradient descent, and then finding these optimal coefficients. But those things still have a sampling distribution. They still did something with the data to get a number. So let's see what that sampling distribution looks like in this case by repeating this many, many times. So let's just wrap this in a let's just do it with numbers. Oh, right. Didn't tell it how many times to do it. Let's do it 1,000 times. Oh, and I didn't get the coefficients out, of course. Okay, so this is our model, right? And now let's say I want to get the coefficient on x. So I can do that with, so let's say if I have this, I can do coef m. And so let me just show you what this does here. So this gives me a vector back with 2 elements corresponding to each of, in this case it's 2 elements because we just have intercept and 1 predictor. But it has as many elements as there are predictors in general, plus the intercept. And if I want to get just the one that corresponds to x, I can do that by either just taking the second element, or if I want to be explicit, I think, I can even index it with the name of the variable. So I'm going to do that one. Like that. Okay. Great. So this is the sampling distribution, and we can make it a little more granular. Okay, So this is the sampling distribution, the approximate sampling distribution, right? Because I only did 1,000 samples, but if I set this number to be really, really big, this will get closer and closer to the true sampling distribution. So this is the sampling distribution of that coefficient for x. And something that you may already be noticing that's interesting is that this happens to have looks like it has a normal distribution. So it turns out that these things are asymptotically normal, these coefficient estimates, which is pretty wild considering how complicated of a function of the data these things are. And so if we want to do now the same kind of inferential statistics that we've done before when we're estimating a mean or a sample covariance or anything else, we know that the process is that we have to first find some kind of formula that, unless we want to do bootstrap, but here we're going to do the kind of a asymptotic normal approximation based inference. We have to find a formula that gives us what is the sample variance or standard deviation as a function of some population parameters. And then we're going to estimate what that number is from the data, right? So the question is, what is the variance of these coefficients? And that's what we need to know if we want to estimate, for example, a confidence interval, right? So for the confidence interval, we would get the standard deviation and then estimate it, plus or minus 2 times our estimate, right? Okay, so here's how this problem has been solved. And this is what you would learn in most classes on regression. So assume this kind of this model here, where x has some distribution, that doesn't matter. But here, the distribution of y given x is assumed to have this form in the population. Okay, so what are the assumptions that are being made here? I've compressed them all into this one little formula, but this is actually several different assumptions. 1, the conditional mean is linear in x, right? So we have the mean of y given x, which is given by this, is this beta 0 plus x beta. That's pretty crazy. I don't know. I mean, unless x is a binary variable, in which case this is kind of always true. But in general, if you have some blood pressure as a function of age, there's no reason why that should go up linearly, right? There's perhaps certain ages where that increases faster and ages where it's increasing slower. So this is a very strong assumption. Second assumption here is that the noise is normal. So you could also write this at noise. You could also write this as y given x is equal to beta 0 plus x beta plus some normal random variable with standard deviation sigma and mean 0. And the assumption is basically that this is normally distributed, right? There's no reason that should be the case, right? There's plenty of measurements that conditional on x. For example, blood pressure doesn't necessarily have to be normally distributed. It could have a longer tail in one direction than another. So that's a little bizarre as well. And the third assumption is that the noise is homoscedastic. So this sigma here is a constant. It doesn't depend on the value of x. So I'll show you actually what we're going to get to this later. But so this is what that looks like. This is what these assumptions look like. So at each value x of the predictors, we have a normal distribution, and that normal distribution has the same width for all the x's. So if that's what the homoscedastic assumption means. We also, of course, have that it is a normal distribution and not some other kind of shape here, and that if you were to plot the means of these normals for each value of x, they all line up along a line like that. So those are the assumptions for deriving what we're going to call the classical standard error. And so given those assumptions, there's some easy math that you can do, and it's algebra basically, but there's kind of algebra, taking expectations, that kind of stuff, evaluating this given the kind of closed form solution for the regression coefficients, which we haven't covered a lot in this class because I don't think it's that useful to know. But if you do that, and you do this kind of algebra, and this is all covered in many other textbooks. ChatGPT can help you with this as well. But I think maybe the best source is the Fox textbook. I think it's called like Applied Regression. It's in the syllabus. If you want to see this kind of thing, or also the Aronow textbook has these things. It's a lot of like matrix algebra. So if you haven't done linear algebra, you don't need the matrix algebra, but it's much more concise if you write these things in terms of matrices and vectors. But suffice to say, you do the math, and given these assumptions, you can prove that this coefficient estimate is normally distributed, which is great because that verifies our intuition that we saw in that simulation there. And moreover, we actually get a formula for the asymptotic variance. For large n, the asymptotic variance of the coefficient is the whatever this sigma is here, that's squared. So it's like the noise variance divided by the variance of x. So this actually, there's a little bit of intuition here. So if you're trying to, let's say, so here's x and here's y. If you're trying to, if you have data, let's say your data look like this. What's the regression fit there? If you do the mean squared error for this is about as good as the mean squared error for this, is about as good as the mean squared error for this. There's a lot of regression lines that you can try to put through there that will all fit about as well, because they're all fitting really badly, right? And the what's going on in this situation where these are your data is that you can see the variance of x is very small, right? Whereas here the noise, this is kind of my sigma squared, is very large. This is actually the conditional variance, y given x. So that's quite large, and this is quite small. And because of that, there's so many lines that are all equally good. And so slight changes in, okay, if I have one more dot here, or if I have one more dot there, then I'm going to get this line versus that line. So slight changes in the data will change my regression coefficient a lot. And that means that the regression coefficient is highly variable, right? It has, the sampling distribution is really spread out. Sometimes you get a big positive number, sometimes a big negative number. You get a very spread out sampling distribution. And that's what this formula is essentially saying, is that if the conditional variance is big, there's more noise, it's harder to estimate the coefficient. You're going to get bigger errors on average. Similarly, if the variance of x is small, that's kind of is going to accentuate that, because the opposite situation is also worth considering. So let's say that the noise is still quite big, right? So we have here a lot. So for this value of x, right, we have data that are kind of spread out like this. It's still quite big. But now we also have, instead of the variance of x being small, let's say x varies over a very wide range. Now we have data like this for this other value of x. Now, if you were to draw a regression line like that, that's clearly much worse than the regression line that goes like this. So even if there's a lot of noise, if the range of x is quite wide, the variance of x is large, then you can get pretty good estimates. Basically, you're kind of explaining away the variability in y with a wider range of variability in x. So it's just a little bit of intuition for what this formula is saying, and how the data generating process relates to the variability of the coefficients. We'll get more into that later. And this, you can of course do a plug-in estimator. This part here, what we're going to do is we're going to take the residuals. So this is my y minus this stuff, and we're going to take the variance of those residuals, because those residuals reflect this kind of additive noise. And for this one, the plug-in estimator is just the sample variance of x. Okay, so this is all quite easy to calculate, and you can do it. And there's also a version with so here I've been talking about beta defined as this single coefficient here. But if x is a matrix of predictors and beta is a vector, so x is like x1, x2, x3, beta is beta 1, beta 2, beta 3. So you can make x into a matrix where you have your rows of data and then your columns that are the different x1, x2, x3. And if you have that kind of setup, you can write it like this. Again, if you haven't seen linear algebra, you're not familiar with this notation, don't worry about this at all. I'm just providing it here for the people who have seen it because it's such a more compact and nice way to write it. And it lets you deal with multiple variables, whereas here, if I had x1, x2, x3, if I were going to try to write this out, it would be a huge mess. Because it would depend on some covariances between x1 and x2 and things like that. But this is the much nicer way to represent it. But it's the same kind of intuition. If you have x kind of spreading around over a wide range, then that counterbalances the effect of a lot of noise in your outcome. And that's great. So let me give you a little bit more intuition for this now, because now this, I'm saying here variance of beta, but beta is now beta 1, beta 2, beta 3. So what I'm actually describing here is the joint variance, or more concretely, the variance of beta 1, the variance of beta 2, and the covariance of beta 1, beta 2. So let me show you what I mean by that. Let's set up this kind of similar simulation that we had before. So now instead of a single predictor x, I have two. I have x and a, and then I have y being generated as some function of x and a, and then I run a linear regression y x plus a, and then I get the coefficients, and I can repeat that many times, and then plot the approximate density of all of those coefficient measurements that I got. So this is just like the each estimate that I get is a point, and then I'm just seeing where those points are clustering, and this is the picture I get. So you see that the coefficients, it's not just that they have sampling distributions, like yes, beta A has a sampling distribution, beta X has a sampling distribution, but they have a joint sampling distribution because they're both coming, you get a pair of them, right? From each experiment that you run, you get a beta A and a beta X, and so those are jointly distributed random variables. If you can think of the population of data sets, right? And then each of those gives you a row of beta A, beta X, beta A, beta X. And so you have your kind of population distribution of beta A, beta X. And that's roughly what we're seeing here. So to describe the kind of variance of this thing, this has a what's called a jointly normal distribution. I think that's discussed a little bit in the challenge assignment, but you don't have to worry about it too much. But it suffices to say that if you have two variables that are jointly normal, you don't only need to describe their individual means and individual variances, but also all of their covariances. And so that's typically written in this kind of a matrix form. So when you see variance of beta hat, where beta hat represents beta 0, beta 1, beta 2, you're asking about the covariance of all of the different pairs. And typically it's written in this kind of matrix form. So you can see in this row here, we have the covariance of beta 0 with something else, beta 1, beta 2, beta 0. And then this row is the covariance of beta 1 with beta 0, beta 1, beta 2. So what I'm varying in each row is the first one, and then in each column is the second one. And of course, you may recognize immediately that the covariance of beta 0 and beta 0 is just the variance of beta 0. So I could have also written variance of beta 0 instead of the covariance of a thing with itself. So on this diagonal, we have the variance of each of the coefficients, and on the off diagonal, we have the covariance of different pairs of coefficients. Again, not really important to know like how matrices work and stuff like that. I'm just kind of saying we're going to see this is important because things in R will output this variance covariance matrix, and so I just want you to know, okay, if I have this matrix, the way that I get, if what I'm interested in is the variance of beta 1, I just need to get this element out of it. And that's how you would do that. Or if I want the covariance of beta 2, beta 1, I just need to get this element out of it. And notice that these two are the same, and these two are the same. So on the off diagonals, it's symmetrical, this matrix. Okay, so that's what we have here. We can get this asymptotic variance covariance matrix. And then essentially, if I have an estimate of this, I could just divide that by n to get the finite sample version. So each of those numbers would be divided by n if I want to get the finite sample version. And that's what you do. So there's formulas for all of that. It's basically given by this. You can implement that in R or MATLAB or whatever and get that done. You don't have to do that. Don't worry. I'm just kind of giving you background. This is what the plugin estimator looks like. That's how you would implement it. So here's what you actually do have to do, which is how do you do this in R? So you will be pleased to see that you don't have to do this plugin estimator, all that stuff. R does it for you. It's very nice. Somebody else already took care of it, so you don't have to worry. You just say M is equal to LM whatever. So here's this insurance data set that we're just using as an example. So you set up your model. We did this last time, and you estimate the coefficients. And then if you want to get inference, you have to estimate the covariance matrix. And there's a function that just does it for you. Okay, so it's called vcov, vcov of M. And so let's have a look at what that does if we plug this into R. Okay, there's our insurance data. So here's our regression model, right? So that gives us the coefficients. Now if we want inference, we do vcov M, and this gives us the the estimated variance covariance matrix. Let me see if I can get it to print. There we go. So it looks like this. So when I was showing you here, what this kind of looks like theoretically, let's say, for example, this element here would be the variance of beta hat 1. That corresponds to this thing here. So this is the variance of the coefficient on this smoker variable. And this is the variance of the coefficient on the age variable, and this is the variance of the coefficient on the sex variable, or rather our estimate of that variance. And these are the estimates of the covariances between the various coefficients. Like this one is covariance between this coefficient and this coefficient. Okay. And we can see, so what I'm showing you here is if instead of trusting vcov, which comes from R, so instead of trusting this, if you actually go and type out all this stuff, how would you do that in R? I've done it for you here. So get N, I make this X matrix. You can see it just looks like this. It's like just the data of the predictors. Then I calculate my various things here, and this matrix that I get out of all of that is the same as if I just ran vcov up to small differences. So don't worry about that. But this is essentially what vcov is doing. Maybe they're dividing by n-1 or something like this. But yeah, it's basically just the plugin based on this equation, because this equation is expectation of a particular thing. So you just do a sample average of that instead and call it a day. Okay, so let's get back here. So what do you do with that? I have this variance covariance matrix. It's maybe a little complicated to get there, but who cares? What can I do with that? Well, you can get standard errors. You can get confidence intervals. So here, for example, get rid of that. Don't need it. So let's say I got my estimated covariance matrix like this. But here I'm extracting the estimated standard error for the coefficient on the smoker variable. So I get, so here this is one way to do it. This gives me the diagonal of that covariance matrix. And then I just want to get the value for smoker yes. And then I take the square root of that to get the standard error, because this is the variance. So if I run that, okay, there we go. And now we can build the confidence interval by taking my coefficient, and then I very simply add two times that standard error, or subtract 2 times that standard error. There we go. So this is the confidence interval on that coefficient, which is this. So remember that these are this is the coefficient charges. Charges is the outcome here, so it's like this amount of dollars for every unit increase. Basically, if you're a smoker, it appears to increase your charges by $23,000. But now we have a confidence interval, so we can say, okay, that $23,000 increase if you're a smoker, that number is just based on the small data set that I had. So if I had a different data set, how different of a number might I have gotten. And here this is saying, okay, it could have ranged, roughly between $22,000 and $24,000. So we're pretty confident that, it's not $20,000, that it's not $30,000, right? So that's the general notion of a confidence interval that we've been working with before. And so this is the long form way to do it. I'm just showing you it like this to reflect what we've been doing before and the kind of manual procedures to build confidence intervals, estimate asymptotic variance, and all that stuff. But actually, there's like a 2-line way of doing it, okay, in R. So you can just go here, and instead of all this stuff, v covariance, blah blah blah, all this you can just load the data, run your model, and then you just type summary of that model, and it does this for you. So it basically calculates the standard error for each of these. It also calculates the p-values based on that standard error, which you also know how to do manually. And if you want confidence intervals, you can do confint m, and this gives you confidence intervals for each of these. So these should reflect what we calculated before, up to maybe some small differences. So that's inference. That's how you do it in R. Now the problem is that all of that is bullshit, because if this is not the truth, that those 3 assumptions are not satisfied, which they never are, then the confidence intervals we get are bad.